So when we last left off our discussion, we were noting resonance effects on proton acidity. And often the most dramatic resonance effects occur when your anion is directly conjugated to a resonance acceptor. So you not only have delocalization of your electron density, but delocalization of your electron density onto a very electronegative or electron deficient atom. So let's compare the following two structures. The structure on the left, so remember how we talked about last session that we can label the relative location of two substituents using ortho, meta, para notation. So this would be para nitrophenol. And we're going to compare it to meta nitrophenol. And my question to all of you is, which structure would you expect to have the more acidic proton? And I'd really like you to focus on thinking, well, what's different between these two structures? And what do the resonance structures look like? How can we delocalize our formed anion's electron density? So let's spend about 3 to 4 minutes on this example. I'm going to pan down a little bit so that way you have space if you want to draw some resonance structures using the annotate tool. And I'd like you to work through this example in about 3 to 4 minutes. And I'd like you to tell me whether the meta or para compound is more acidic. So O, otherwise known as ortho, is used to name a compound if you have a substituent at the 1 position and a substituent at the 2nd carbon going across the ring. Meta is used if you have a 1-3 relationship, while para is used if we have a 1-4 relationship. Did that address your question? It's not needed to solve this problem because I've given you the structures, but this is an important general effect to consider. And this will pop up a lot if you have a resonance withdrawing group at the para position. So let's work through this example, and in about 3 to 4 minutes, we'll discuss. I'd like you to tell me, using your drawn resonance structures, which of these two compounds is more acidic? And don't be shy to submit your responses and questions in the chat, or submit your responses or questions verbally. And we'll discuss this example in about another 2 minutes. And let's try to get some proposed responses in the chat for which of these two structures would be more acidic. So inductive effects are one component, yes, but if you look at these two structures, is there a difference in their resonance effects on anion stability? So let's spend about another minute to a minute and a half on this example, and don't be shy if you want to draw using the annotate tool a resonance structure that would help us process and work through this problem, or a resonance structure that would help support your argument for which compound is more acidic. So let's discuss this example. So presumably if we generate the conjugate base of each of our two compounds, let's then focus on assessing the relative acidity of each of these two compounds. As we can see quite clearly, we can delocalize our electron density, not just through our aromatic ring, but into our nitro group. So the anion for the para compound experiences a significant amount of resonance stabilization and delocalization as we are delocalizing our electron density into a very electron deficient set of atoms. Okay, so let's look at what happens when we have the meta substituent. We actually looked at a case almost exactly identical to this last class session. So no matter how hard we try, what ultimately we'll see if we try to draw out the resonance structure, we are not able to delocalize our electron density into our electron deficient nitro group. So that in turn gives us the following. Let's just look at this representative resonance structure as it really brings home this idea that we cannot delocalize our electron density via resonance into our nitro group for our meta compound. So as a result, considering these resonance effects, which of these compounds has the more stable conjugate base anion and as a result is more acidic? The meta or the para compound? The para compound, exactly. So this is pretty commonplace analysis for relative acidity of two compounds, accounting for resonance effects. Resonance effects are typically more dramatic than inductive effects if there is a small difference in the position of your substituent. So the para isomer or the para compound is more acidic. And it's more acidic by orders of magnitude, by about 4 pKa units. So it's a pretty dramatic effect. Does this example make sense? Any questions on this example? If not, let's keep going and let's talk about other factors affecting acid strength. Now, this factor is pretty straightforward, charge. So charge has a huge effect on acid strength. The larger the positive charge on an atom, the more acidic the protons attached to that atom are. So for example, H3O plus has a pKa of around negative 1.7, while H2O has a pKa of 14. So atom charge dramatically affects the pKa of protons attached to that atom. So, likewise, the larger the negative charge on an atom, the less acidic the protons attached to the atom are. So, my question to all of you, if we look at these two structures, considering our molecule on the right already has a negative charge, if we compare the pK of this proton, following this logic, which proton would you expect to be functionally more acidic? Which proton would you expect to be easier to remove? From the neutral species or from the anionic species? From the neutral species. The neutral species proton is easier to remove. Remember, this proton has a pKa of roughly 22 to 25, while in order to remove this proton, typically you need a very strong base. For example, butyllithium, where the conjugate pKa is around 50. So it's pretty difficult to take an anionic species and subject it to additional ionization. So in general, cationic species, the protons attached to that cationic atom are more acidic. For anionic species, it is substantially more difficult to remove a proton from an anionic species, and as a result, their pKa values are larger than you'd expect, which means they're less acidic than you'd expect, looking at the neutral version of that compound. Does that make sense to everyone? Does this idea make sense? Any questions on this idea? Okay, so let's keep going then, and let's talk about ranking these effects on acidity. So this is in order of importance, but this is not 100% definitive. You will see some exceptions depending on the magnitude of these effects. First, charge, that's the big one. It has the largest effect on acidity. The next is atom electronegativity and atom size, which can be summarized as atom effects. Remember, from atom effects, anions in general are more stable on large electronegative atoms, and atomic size has a larger effect on anion stability. The larger your atom, the more it is able to stabilize a negative charge over a larger region of space. Do these examples make sense to everyone? Do these examples make sense? Does this look familiar to everyone? Okay, let's keep going now. So in terms of resonance, resonance has the next most dramatic effect on pKa values. If the conjugate base is stabilized via resonance, the acid in turn would be more acidic. We can see this if we compare a normal alcohol to a carboxylic acid, where a carboxylic acid is stabilized via resonance and also atom effects for that matter, and that results in a pKa value that is order of magnitude smaller, so we're order of magnitudes more acidic for our carboxylic acid. Does this look familiar to everyone? Any questions on this overview? Continuing on, the next major effect is induction. So quite simply, in inductive effects, Let me draw out. Sometimes the structure drawing tool likes to modify the structures that I've pasted in. So electronegative groups adjacent to acidic protons increases the proton acidity by stabilizing the conjugate base anion. Inductive effects are both distance dependent as well as dependent on the number of electron withdrawing groups and the electronegativity of the electron withdrawing groups. As we notice, addition of electron withdrawing groups results in a substantial drop in pKa. Does this section on inductive effects look familiar to everyone? Does this section on inductive effects look familiar? Any questions? The next major effect, which is pretty closely tied with inductive effects, are orbital effects. Anions are more stable if the lone pair electrons are in a lower energy orbital. This is why anions are more stable in sp orbitals compared to sp3 orbitals. And we see this by a commensurate drop in pKa value and a commensurate increase in acidity when we have an sp hybridized atom with a potentially acidic proton. So if we compare proton acidity as a function of hybridization, we see that the sp hybridized atom has a proton that is substantially more acidic. The reason for that, the anion is more stable in the sp hybridized orbital. Does this make sense to everyone? Does this look familiar to everyone? The last effect, and it's pretty minor, has to do with solvation. So the less steric congestion around an acidic proton, the more acidic the proton. Remember, the reason for that is because we want to be able to effectively surround our proton with solvent. And if there's a really bulky, sterically hindered group around our acidic proton and around our potentially anionic atom after ionization, then in turn the anion is less stabilized by our solvent, and in turn the anion, because it is less stable, is less likely to form in significant amounts, and our proton experiences a larger pKa and is less acidic. Does this make sense to everyone? So we're going through an overview of all the different effects on proton acidity. And now that we have all of these effects considered, we're going to have to consider how these effects can interplay with each other, how these effects should be considered when you have multiple different effects that you need to consider at once. So let's try to ask the question, which of the following compounds is more acidic? We know from our pKa table, what is the pKa of acetylene? So if we go to our pKa table and we find acetylene, everyone has a copy of their pKa table. An alkyne proton has a pKa of around 25. Okay? An amine, what is the pKa of an amine from our table? What is the pKa of an amine? Roughly 35. Okay? This example is pretty interesting because if we think about our hybridization, we're comparing an sp to an sp3 atom, but we're also comparing nitrogen as our atom versus carbon. So in this case, what effect wins out? Atom effects or orbital effects? Which effect has a greater impact on our overall acidity in this case? Sorry. So typically, yes, atom effects have the greater effect. But in this example, in this specific case, orbital effects dramatically impact pKa. And the reason why I chose this example is because it showcases that the ranking in terms of effects on proton acidity are guidelines. You will have to consider all of these effects when you're thinking about proton acidity. So as we can see, even though we'd expect the ammonia to be more acidic from the perspective of atom effects, in this case, because there's a substantial difference in the hybridization of our two atoms, the alkyne proton is substantially more acidic as a result of these orbital effects. Does that make sense to everyone? Perfect, perfect. So the interesting thing is, if we consider the following example, let's try to see, is the reaction going to be product or reactant favored? So we have a pKa of around 25 compared to a pKa of around 35. Can you use this? Can we use the following nitrogen-centered anion to deprotonate our alkyne? Is this reaction product or reactant favored, looking at our pKa values? Is this product or reactant favored? Can we actually execute this reaction in the lab? What does everyone think? Product or reactant favored? So we have our pKa values. So we see that ammonia is less acidic than our alkyne. So we'd expect this reaction to be product favored. Does this make sense to everyone? Does this look familiar to the examples that we did at the start of this chapter? Okay, so let's look at another example. And I'd like you to tell me which of these protons is more acidic. So we'll give us a whole list. So A, B, C, D, and E. Which of these protons would you expect to be the most acidic? Considering all of the effects that we have discussed so far in this class. So let's take about 2 to 3 minutes and let's try to get some assignments for the most acidic proton in the chat. So let's try to answer the question, which of these protons would we expect to be the most acidic and why? And if you have any questions or if you want to submit your response, don't be shy to use the chat feature or ask a question or propose your responses verbally. So let's try to get some proposed responses, and we'll continue working on this example for about 2 minutes. And let's try to get some proposed responses in the chat or verbally. So we have a proposal for proton A. Do we have some other proposals for the most acidic proton? It's fine to agree with your classmate, and it's also fine if your response disagrees with your classmate. Let's try to get a pool of responses, and we'll discuss this example in about 1 minute. Let's try to get a few more responses in the chat before we discuss this example. Okay, so let's talk about this. So we see a lot of proposals for A, but let's really focus on the Y. So you can make the argument from an inductive effects perspective. That's perfectly reasonable. Well, this proton is also experiencing some inductive effects for that matter. Likewise, proton B and proton C for that matter. So I can't see how inductive effects would be a complete explanation, but it's a good to consider. That's one thing that we do have to consider. The other effect that we have to consider is resonance effects. So if we remove proton A, we can delocalize our electron density across an oxygen and an oxygen atom. So we can delocalize our electron density across very electronegative atoms. Proton D looks pretty suspicious to me because it has some pretty monstrous inductive effects. However, if we think about our resonance effects, for proton D, we're able to delocalize our electron density over an oxygen and a carbon atom. So if we think about resonance effects from the context of atom effects, we would expect proton A to have greater amounts of resonance stabilization of our anion because, and this is the part that's really important, our electron density is delocalized over electronegative atoms. And these resonance effects will be stronger than your inductive effects in most cases. Does this argument make sense to everyone? So it's not just important to be able to assign acidity, but also present a cogent argument that considers all of the different aspects of this problem. Does that make sense to everyone? Any questions on this example? If not, let's keep going now. And let's work on these two examples. I'd like you to tell me which of these protons is more acidic. So we have A and B in our first example and C and D in our second example. And we'll discuss this problem in about 3 to 4 minutes. So I'd like you to propose which of these protons for each of these two problems would be more acidic. And notice how the structures don't necessarily have to be in your pKa table for you to apply the rules that we've discussed for looking at structures and assigning relative pKa. And we'll discuss this example in about 3 to 4 minutes. And don't be shy to submit your questions and responses in the chat or verbally. I'd like to see a few responses before we discuss. So we have a proposal for A and D on the basis of resonance effects. And I would consider for the second question whether proton C, when it is removed, whether that anion can experience resonance delocalization. So let's keep working on these examples. So it's good that we have not only a proposal, but a logical reason for why each of these protons is more acidic. We're starting to develop that skill. So let's keep working on this example and we'll discuss in about another minute to a minute and a half. I really encourage you to share your opinion and perspective on each of these problems, as it helps me understand what the class is thinking and provide more directed feedback. So we have some responses in the chat. So let's take a look at these examples. So if we compare proton A to proton B, we have the argument that proton A is more acidic on the basis of resonance effects. Well, if you're going to make that argument, it's important that you draw out your actual anion and check to see if it can be delocalized. In this case, we can clearly see that we can delocalize our anion into both of our adjacent pi systems. So we can really think of the conjugate base after removal of proton A to look something like this, where our negative charge is distributed across multiple atoms, many of which are electronegative. If we consider proton B, we can experience delocalization via resonance, and we can stabilize our electron density, but we're constrained in that delocalization only really occurs over 3 atoms. We have this, unfortunately, sp3 hybridized carbon getting in the way of a fully conjugated system. So as we can see, the conjugate base generated from A experiences a greater amount of stabilization via resonance delocalization. Ergo, proton A is more acidic. Does that argument make sense? Okay, so let's look at our second case. So we have 2 protons, and suppose that we generate our conjugate base anion. We are able to delocalize our anion across multiple electronegative atoms, in this case, 2 oxygen atoms. If we look at proton D, we are able to delocalize our electron density over 2 nitrogen atoms. Now, my question to all of you is, from the perspective of atom effects, which atoms have a greater effect on anion stability? Electronegative atoms or less electronegative atoms? Which atom would be more readily able to stabilize our negative charge? Oxygen or nitrogen? Oxygen or nitrogen? Oxygen, exactly. So we'd expect proton C to be more acidic because both of these structures are experiencing resonance stabilization. However, proton C is delocalizing its electron density over more electronegative atoms. Does that make sense? So just for comparison, the pKa of a carboxylic acid is about 4.2, while the pKa of this urea proton is around 15. It is way more acidic than your typical amine, but not by much, but it's still not more acidic than a carboxylic acid. Does that make sense? Any questions on this example? Let's keep going now, and let's try to assign which of the following protons is more acidic. And not just which of these protons is more acidic, but why. So comparing proton A and proton B, I'd like you to provide a reasonable argument for which proton is most acidic. And we'll discuss this example in about 2 minutes. And if you have any questions when working through these problems, don't be shy to ask them in the chat. So let's try to get some proposals in the chat, and then we'll discuss this example in about another minute to a minute and a half. So it looks like we're starting to see a consensus for proton B. Let's entertain a few more additional responses, and we'll discuss in about another 30 seconds to a minute. And don't be shy to contradict your classmates if you have a reasonable explanation for which proton is more acidic. The more responses we have, the more I can provide directed feedback to address your question. Okay, so we have a tentative assignment that proton B is more acidic. Well, let's look. So for proton A, we have your typical amide structure. And now this is partially where we have to consider a few things about the anion generated. So suppose we do generate an anion. One of our lone pairs is going to be localized on an sp2 nitrogen, while the other lone pair is delocalized. So amides don't get a ton of benefit from resonance effects because one of the lone pairs, is always inherently going to be localized on the nitrogen atom. If we compare that to the following motif, commonly found in many sulfonic acids, if we look at the conjugate base, as you can see, we are able to readily delocalize our electron density across multiple highly electronegative atoms. This presents a very, very strong stabilizing effect as a result of this delocalization, and because our anion obtained by removing proton B is very stable, proton B is more acidic. Does that make sense to everyone? Any questions on this example? Any questions? Oh, the pKa of proton B, I'd estimate that this pKa, well, we have some data to back that up. Let's look. So the sulfonic acid has a pKa of about -1. Very acidic. So we always have the tools available to answer our questions. And it's not too surprising. It's the same motif found in something like sulfuric acid, for example. It's quite acidic. While if you wanted to look for the amide, let's find the amide proton. It's a bit of an esoteric idea because you're not typically going to be removing that proton in most reactions, but let's see if we can find it. It's not on the table. Let me do a quick search to give you some information on the relative pKa of an amide proton? So I guess I don't have the direct pK table. Let me see if I can find a reference for that can answer that question really quickly. The amide pK is approximately 17, give or take. Similar to our urea proton. This is partially why you don't see protonated amides as well, as they're substantially more acidic than you would expect. Any questions on this example? Okay, let's keep going. This is always a fun example to look over. I'd like you to tell me which of these three, rank the following three protons, A, B, and C, in order of increasing acidity. So which proton is the most acidic? Which proton is the least acidic? So let's spend about 3 to 4 minutes on this example, and then we'll come together as a group to discuss. And remember, try to have a logical basis to justify your ranking. And we'll discuss this example in approximately 3 to 4 minutes. And if you have any questions, don't be shy to submit your responses and any questions that you have in the chat or verbally. And let's try to get some rankings in the chat for the relative acidity of each of these three protons before we discuss. And the same factors that we use to assess proton acidity will also be used later on to assess anion stability and anion nucleophilicity, or the ability of an anionic species or a species containing a lone pair to engage in nucleophilic substitution reactions. So let's try to get some responses in the chat for the relative ranking of the acidity of each of these compounds and each of the protons found in this compound. And then we will discuss in about another 2 to 3 minutes. So we have our first proposal in the chat for the relative ranking of each of these protons in order of increasing acidity. Let's try to get a few more responses in the chat, and then we'll be able to discuss this example. So let's try to get a few more responses in the chat before we discuss. And make sure you have a logical basis to back up your argument. I noticed in the chat there was a mention that after you remove proton B, that species can participate in resonance. And I would always like you to keep in mind what orbital is our lone pair being placed in. So we'll discuss this example in about another 1.5 to 2 minutes. And let's try to get some more responses in the chat. So we have a wide range of different potential responses. Would anyone else like to chime in with their proposed response for the ranking of proton acidity for these 3 protons? And we'll discuss this example in about another 30 seconds to a minute. Do we have any other responses before we discuss this example? Any other responses to consider before we discuss this example? I find the act of vocalizing your response and sharing your response can help you revise and adjust your perspective when discussing later problems. If not, let's discuss this example. And let's talk about the relative ranking of acidity for each of these 3 protons. Let's talk about the relative ranking for each of these 3 protons. So first, let's draw some conjugate bases. So if we look at proton A, so we can delocalize our anion via resonance. However, we don't exactly delocalize our anion over very electronegative atoms. So we're able to delocalize our anion over 2 carbon atoms. Okay. If we look at proton B, that proton is pretty stuck. It's localized in an sp2 orbital, and it's stuck on a carbon atom. So we'll talk about this later, but this proton is localized. This lone pair is localized. So removing that proton would generate an anion in an sp2 orbital. Finally, let's look at proton C. Proton C, we would in turn generate an anion on a very electronegative nitrogen atom that we can in turn delocalize across 2 very electronegative atoms. So proton C is definitely the most acidic here. And now we have to think which of these 2 protons, A or B, is most acidic. And this comparison has some interesting pedagogical value because we're essentially comparing the acidity of a vinyl proton to an allylic proton. So let's see if our pKa tables can provide us any rationalization that we can use. So the proton directly attached to our typical alkene has a pKa of approximately 43. Okay? So this proton has a pK of somewhere around 43. Okay, what about an allylic proton? Let's look and see. Let's look and see if we have any clarification for our allylic proton. So nothing directly in the table, but we can make an argument that would seem reasonable from the perspective of resonance effects. So the argument that we're going to make is as follows. If we're thinking about the conjugate base generated from proton A, what is the hybridization? So the hybridization of the carbon atom in this case is sp2, and our lone pair is found in a delocalized conjugated p orbital. And my question to all of you is, which effect would you expect to be more pronounced? The orbital effect as a result of this sp2 carbon containing a lone pair in an sp2 orbital, or resonance effects, where we're delocalizing our lone pair over multiple atoms that are conjugated via resonance? Which effect would you expect to be more pronounced? Which effect would you expect to be more pronounced? The resonance effects. And we actually see this. The allylic proton has a pKa of around 42. So the resonance effects trump the atom effects. It's a very subtle difference, but it's important to pay attention to. Does that argument make sense to everyone? Does that argument put forward make sense? So we're arguing that resonance effects have a greater effect on anion stability, which would result in a more acidic proton A, and proton B is the least acidic because it's a localized lone pair in an sp2 orbital. So A and C experience resonance stabilization, which results in a more stable anion, which results in a more acidic proton. Does that make sense to everyone? Does that argument make sense? Perfect. The distinction between A and B is subtle, but you should be familiar with and you should be comfortable explaining the difference between a vinylic and allylic proton. Allylic protons are more acidic, and allylic protons in general are easier to remove. Does this example make sense? Perfect. So let's keep going now. And let's talk about a really important skill that I want everyone to be able to utilize, because it's something that you're going to practically have to do when you're developing solvent screens and figuring out and designing reasonable reaction schemes. So this is the idea of choosing the correct reagent for a deprotonation reaction. So in general, we know that if the reactant acid has a smaller pKa, the reaction is product favored. If the product acid has a smaller pKa, the reaction is reactant favored. You can also look at reactions from the perspective of conjugate base stability. So if the base is less stable than the conjugate base, the reaction is product favored. If the conjugate base is less stable than the reactant base, then the reaction is reactant favored. That's another perspective you can use. So our classic example, we compare acetic acid and water. Hydroxide ion is less stable than acetate because it's not able to experience resonance delocalization. Acetic acid is more acidic. Both of these factors suggest the reaction is product favored. Now, this same process can be used to deliberately choose an acid or base to complete a reaction. And that's what we're gonna develop here. That's what we're gonna develop here. We're gonna look and assess the position of an equilibrium for various chemical reactions between and acid-base reactions between two compounds. And then what we're gonna do is we're gonna decide and choose reagents to generate a desired reactant or product. So we're going to carefully choose our acid and base to manipulate where this equilibrium will prefer to lie, whether it's going to prefer the reactants or the products. So for now, let's look at this first example. We're just asked to predict the position of equilibrium for the following reactions. Now, it's important, rather than just going straight to the pKa table, things may not show up in the pKa table. So your goal is to think, what is different? And the main thing that's different is this entire comparison essentially boils down to oxygen versus sulfur. And which of these atoms has a larger atom effect? Which of these atoms can more effectively stabilize an anion? Sulfur, exactly right. So in turn, because we can delocalize our electron density into our sulfur, and because sulfur is more readily able to stabilize a negative charge, this base is more stable than this conjugate base, for example. So what you're doing in this case, what you're doing when you're predicting the position of equilibrium is you are comparing your base and the conjugate base and determining which species is more stable. Because our base is more readily able to stabilize its anionic charge, our base is more stable, and in turn, what that means is that our conjugate acid is more acidic, while our original acid is less acidic. So you're doing a head-to-head comparison. You're doing a head-to-head comparison between the base and the conjugate base and the acid and the conjugate acid. And because the product acid is more acidic, would we expect this reaction to be reactant or product favored? Would we expect this reaction to be reactant or product favored? Considering our reactants are generally more stable. Considering our reactants are generally more stable and not very acidic, would we expect this reaction to be reactant or product favored? What does everyone think? Let's try to get a few more responses just to make sure everyone's comfortable with this. This would be reactant favored, right? Because our acid is less acidic and our base is more stable than our conjugate base. Does that make sense to everyone? Does that make sense? Just like before, as a general rule, the weakest acid is favored. Okay, so let's try another example. And I'd like you to tell me and predict the position of the equilibrium for the following reactions. This is known as your typical equilibrating conditions to form an enolate anion. So I'd like you to consider the pKa values of each of our protons, consider the relative stability of your base and conjugate base, and I'd like you to tell me which of these species is more acidic, and in turn, where does the equilibrium lie? Does it favor reactants or products? So I'll give everyone about 3 to 4 minutes on this example before we discuss. And don't be shy to use your pKa table if you feel like it would help you. So let's try to get some proposals in the chat. Which is this equilibrium reactant or product favored? And be really careful about looking up your pKa values. We have our first impression, but let's try to verify our first impression by actually checking the pKa values. Just as a hint for everyone, this proton has a pKa of approximately 25. This proton has a pKa of approximately 18. With that information, how would we like to revise our predictions? With that information, how would we like to revise our predictions? So we have a lot of students saying that this reaction is reactant favored. That's exactly right. And we can rationalize this from the perspective of atom effects. So we're comparing an oxygen-centered anion to an anion that is partially centered on carbon. And oxygen is more readily able to stabilize a negative charge. And note, because this lone pair is delocalized, it spends some portion of its time sent on and localized around the oxygen atom. However, the electron density is also left on carbon, which is notoriously poor at stabilizing electron density. Does this argument make sense to everyone? Now, of course, this picture neglects concentration effects and stoichiometric effects. If you add a ton of base, you can eventually force this reaction and force this equilibrium to generate a reasonable amount of product. But just looking at this equilibrium overall, we see we're fighting an uphill battle here. And so we may need to modify our conditions appropriately. Does that make sense to everyone? Does this example make sense? So it's important to really pay attention to what's going on in the reaction, because the reaction conditions tell you a lot about how the reaction should be run and practically what you need to do in order to make a reaction slightly favorable. Okay, so let's keep going now, and I'd like you to predict the position of equilibrium for the following reaction. So I'd like you to tell me, looking at these two compounds, whether this reaction is reactant or product favored, whether this equilibrium set of reactions is reactant or product favored. And this, you don't even have to look at your pKa table, though if you have it memorized, it certainly helps. Knowing pKa values offhand can save you a lot of time on exams. And let's try to get a few more responses in the chat, and we'll discuss in about a minute to a minute and a half. So what does everyone think? Is this reaction reactant or product favored, and why? Let's try to get a few more responses in the chat before we discuss in about 30 seconds. Okay, so looking at our two anions, we see our product anion, which is the conjugate base, is stabilized via resonance. And as a result, this conjugate base is more stable, and as a result, our acid is going to be more acidic because it generates a very stable conjugate base. So then, with this information in mind and adding in the pKa values, pKa of about, say, around 17, pKa of around 9 to 10. Is this reaction reactant or product favored? Reactant or product favored? It would be, of course, product favored. not only is our starting acid more acidic, but our conjugate base is more stable than our reactant base. Does this argument make sense to everyone? Does this argument make sense? Okay, so let's do one last example to close out today's session. I'd like you to tell me the following compound is a fluorescent probe for the cyanide anion, and it relies on a pretty ingenious trick that when cyanide attacks the probe, you generate an anion that is in equilibrium with the following conjugated anionic species. And this conjugated anion has a unique color and a unique fluorescence profile. I'm just going to indicate that you'll be able to see generation of light when this compound is generated and when this compound is excited. So my question to all of you is, does this equilibrium favor our reactants or products? Does this equilibrium favor our reactants or products? So just like we can have intermolecular proton transfer, we can also have intramolecular proton transfer. And don't be shy to submit your responses in the chat, and we'll discuss this example in about another 2 to 3 minutes. And if you have any questions working through these problems, don't be shy to ask them in the chat or verbally. And we'll discuss in about another 2 minutes. And let's try to at least get a few responses. And what this problem boils down to is just a direct comparison between this phenolic proton and this normal, relatively normal alcohol proton. So I'd like you to tell me which of these protons is more acidic, and as a result, is this equilibrium reactant or product favored? What does everyone think? Let's try to get at least a few responses in the chat before we discuss. So we just established, right, that the phenolic proton has a pKa of around 9, right? Well, your typical alcohol proton has a pKa of around 16 to 17, right? So then, where is this equilibrium going to favor the reactant or the product? It would be product favored, exactly. And that's why this probe actually works, because after attack of cyanide, this anion is more basic than our conjugate base. So it undergoes a proton transfer to generate this conjugated anion, which when excited is capable of emitting light, undergoing fluorescence. So we can use this probe as a way to detect cyanide in solution. So a practical application and a clever application of a designed molecule that can undergo a specific product-favored acid-base reaction. Does that make sense to everyone? So this showcases how deliberate design of your molecule can allow, and preparation of a molecule with a very well-defined and specific structure can allow you to create a molecule that is usable for a very well-defined and quite useful purpose. Any questions on this example, and any questions before we close out today's lecture session? So